We are surrounded by complexity that we just take for granted. Think
Mm.
about the phone in your hand or the screen you might be looking at right now. All of that is powered by microchips. It's displayed on these incredible high-resolution screens. These things, they don't just define the modern economy, they define modern life itself.
But here's the thing. Almost nobody stops to think about the massive, hyper-precise, and just astronomically expensive infrastructure it takes just to make those things.
Right.
We're not talking about Intel or Samsung, the companies that design and sell the final chips. We're talking about the company that sells the machines that build the entire digital world.
Exactly. And that's where we're going today. We're doing a deep dive into Applied Materials, Inc., or AMAT on the stock exchange. This is the ultimate invisible giant.
It really is. They're headquartered in Santa Clara, California, but their reach is completely global. They provide the absolute fundamental equipment for pretty much every piece of advanced electronics made anywhere on Earth.
When you say fundamental, you really mean it. AMAT is critical infrastructure.
Absolutely. They supply the tools, the services, and all the specialized software you need to manufacture integrated circuit chips, flat panel displays. I mean, everything from the tiniest smartphone to the biggest TV.
And even specialized coatings for things like flexible electronics and advanced packaging.
Yep, all of it.
So our mission today is to really pull back the curtain on this behemoth. We want to understand their technological core. What are these multi-million-dollar machines actually doing on a silicon wafer?
And then we'll track their history, it's a really dynamic story of growth, huge acquisitions, and some pretty spectacular high-profile failures.
And then critically, we have to connect all of those dots to what's happening right now. Because the sources show a company that is sitting right at the most critical and honestly the most dangerous intersection of the modern global economy.
The stakes just couldn't be higher. And to understand why AMAT is so central to global conflict at this very moment, you have to get a sense of their sheer scale.
So let's look at the numbers.
Based on the 2025 financial data, this is a titan. It's pulling in US $28.37 billion in revenue.
Wow.
With a net income of almost $7 billion. That's US $6.998 billion. And they have a dedicated global workforce of 36,500 people.
And of course, they're a component of both the S&P 500 and the NASDAQ 100. This is not some small niche player.
No, not at all. This is the engine room of global technology.
And as we often remind listeners, many people have heard of the Dutch company ASML because of their crucial lithography machines. But Applied Materials is the second largest supplier of semiconductor equipment in the world.
They are completely indispensable. And that indispensability is exactly what we need to unpack.
Okay, so where do we start?
Let's start with how they've structured this global operation. They basically have three pillars to their business, and then we'll dive deep into Pillar 1, which is the Semiconductor Products Group. That's the heart of all their technical expertise.
Let's do it. Let's jump straight into that technical core.
Yeah.
Because I think if you want to grasp why the U.S. government cares so much about what AMAT sells to China, for example, you have to appreciate the sheer complexity of what their machines can do.
Absolutely. So Applied Materials organizes its sprawling business into three major sectors. And they also have a really important venture investing arm called Applied Ventures, which is always scanning the horizon for the next big thing.
But the money's in the first pillar.
The vast majority of that $28 billion in revenue is generated by Pillar 1, Semiconductor Products. This is the division that develops and builds the highly specialized equipment used in the most intricate phases of creating a chip. We're talking about the wafer fabrication steps.
I think the best way to visualize this for everyone listening is to imagine the silicon wafer not just as a flat disk, but as a three-dimensional blueprint that's built up layer by atomic layer.
That's a great analogy.
It's not an assembly line in the traditional sense. It's like the most sophisticated molecular construction site humanity has ever come up with.
That's a perfect way to frame it. And AMAT provides the entire toolkit for that construction site. To really simplify the process, all the incredibly sophisticated machines they build fall into three basic categories of action.
Okay.
You're either adding material, modifying that material, or you're removing and polishing that material.
Okay, let's start with adding material. The sources say AMAT calls this deposition. This seems to be where their core strength really lies. What are the key processes here?
So we're talking about a whole alphabet soup of acronyms, but the main ones are atomic layer deposition, or ALD, chemical vapor deposition, CVD, and physical vapor deposition, PVD.
Okay, let's break those down. What are CVD and PVD?
You can think of CVD and PVD as the workhorses. They've been around for a while. CVD uses chemical gas reactions inside a chamber to literally grow a thin film on the wafer surface.
And PVD?
PVD is a bit different. It uses a process called sputtering. Imagine blasting a solid target of, say, copper or aluminum with ions in a vacuum so that tiny particles vaporize and then coat the wafer.
So they're both essential for laying down the different layers you need in a chip. The conductive wires, the insulating materials, all of that.
Exactly. They are absolutely fundamental.
But the real game changers, especially in the advanced chips where all the geopolitical tension is focused, seems to be ALD, atomic layer deposition. Why is that process so critical right now?
This is where AMAT earns its geopolitical relevance. Modern chips are no longer flat, two-dimensional structures.
Right, we've moved into 3D.
We've moved into 3D architectures, first with FinFETs and now with what we call gate-all-around or GAA transistors. These designs have vertical fins, incredibly deep and narrow trenches. I mean, the topography is insane.
So you can't just spray a layer of material on top and hope for the best.
You absolutely can't. When you need to lay down a perfect insulating layer or a conducting gate material inside one of those tiny deep features, traditional CVD or PVD just won't work. The material won't conform uniformly to that complex 3D shape. You'll get more on top and less on the bottom.
And if the material doesn't conform perfectly, the transistor fails. The whole chip could be useless.
Precisely. ALD solves this problem. It uses alternating chemical pulses, where each pulse reacts with the surface, coating it one single atomic layer at a time.
Wow.
Imagine trying to paint the inside of a microscopic winding cave with such precision that every single internal surface, every nook and cranny, is coated with exactly the same thickness of paint.
That's incredible.
It is. AMBAD's ALD tools allow chip makers to build things like high dielectrics and other essential materials with these ultra-thin, perfectly uniform films. That guarantees the performance and the reliability of those 3D transistors.
So the ability to do this consistently, at scale, across millions of wafers, is foundational to every modern logic and memory chip.
It is, and this is why AMAT's specific tool sets grant them, frankly, a chokehold power in the industry.
Okay, so that's deposition, or adding material. After we've deposited the layers, we move into the refinement modification phase.
Yeah.
The material is there, but it's not functional yet. How does AMAT's equipment actually change it?
The two main processes here are rapid thermal processing, or RTP, and ion implantation.
Let's take RTP first. What does that do?
RTP is a crucial step that happens after you've deposited material or etched some features. Those processes can be really violent at a microscopic level, and they can damage or stress the silicon's crystal structure.
Okay.
So you need to heal it. You have to heat the wafer to very high temperatures, sometimes up to 1,000 degrees Celsius. But, and this is the key, you have to do it incredibly quickly and precisely in just a few seconds.
Why so fast?
Because you need to repair those crystal defects or activate the dopants you've introduced without letting the heat spread and damage all the delicate surrounding layers you've already built. So AMAT's RTT tools are all about lightning fast, highly controlled heating and cooling cycles.
And then there's ion implantation. This sounds like where the chip actually becomes programmable. Is that right?
That's exactly right. This is really where the magic happens. You're turning raw, inert silicon into a semiconductor. Ion implantation is literally a high-energy particle accelerator that fires specific ions like boron or phosphorus directly into the wafer's surface. These ions are called dopants. They penetrate the silicon lattice and change its electrical properties.
And that's what creates the different types of silicon.
Yes. It defines whether a specific area will become P-type or N-type silicon. And without that distinction, you cannot create the diodes and transistors that form all the logic gates. This is a fundamental step.
And the sources note that AMAT made a huge move in this area with a major acquisition.
They did. They bought Varian Semiconductor back in 2011, which was a huge deal, and made them a full-service provider of these critical modification tools and really solidified their market position.
Which brings us to the final category, shaping and finishing. Once you've layered, doped, and healed the wafer, you have to actually carve the circuits and then polish the surface to get ready for the next layer.
Right. This involves two key processes, etch and chemical mechanical polishing, or CMP.
Etch is the carving part.
Exactly. AMAT provides plasma etch tools that selectively remove layers of material. They usually follow a pattern that's been laid down by a lithography machine.
So this is how you create the actual circuit pathways.
It is. Etch is how you create those deep vertical trenches and complex high aspect ratio patterns that define the wiring of the chip. It's incredibly precise subtraction.
And then there's CMP, chemical mechanical polishing. Now this sounds like the simplest step, just polishing something. But in a 3D chip environment, that must be an immense engineering challenge.
It is arguably one of the most critical processes for maintaining yield, or the percentage of working chips, in modern manufacturing.
Why is it so important?
Well, think about it. By the time you're done, you might have dozens or even hundreds of layers on a wafer alternating between tiny copper wires and insulating materials. The surface inevitably develops tiny bumps and valleys. It's not perfectly flat. And if that surface isn't absolutely perfectly flat before you try to pattern the next layer, your lithography step won't focus correctly. The light will be distorted, and the entire multi-million-dollar wafer will fail.
So, to use our earlier analogy, you have to polish the surface of a microscopic skyscraper perfectly flat every 100 feet so you can build the next 100 feet without the whole thing collapsing.
That's a fantastic way to put it. That's exactly right. CMP uses a chemical slurry combined with a high-tech polishing pad to polish the wafer surface down to a near-atomic level of flatness.
Across the entire 300-millimeter disc.
Across the entire disk, AMT's CMT equipment ensures that uniformity, which is absolutely essential for maximizing the number of working chips you get from every single wafer.
It's clear that their semiconductor product sector isn't just about making one-off machines. It's about providing the entire integrated capability for the most advanced manufacturing possible.
Right.
And you can't make a chip if you can't verify the quality at every single step. That must be a huge part of their business, too.
Yield is everything in this business. A single microscopic defect can ruin a wafer worth a fortune. So way back in 1996, AMAT made a strategic move and acquired two companies, Opal Technologies and Orbot Instruments, for a combined $285 million.
And what was the goal there?
The goal was specifically to establish leadership in yield enhancement. These acquisitions gave them the tools for high-speed metrology, which is just a fancy word for measuring critical dimensions, and for inspecting the patterned silicon wafers and masks. It's the insurance policy for the entire fabrication process.
So their strategy in this pillar is just aggressive growth through consolidation.
Yes. And that brings us to the planned purchase of Kokusai Electric, the $2.2 billion deal that ultimately fell apart. That planned acquisition shows AMAT's constant desire to consolidate their deposition capabilities even further.
And we will definitely come back to why that deal failed. It's a huge part of the story.
It is. Kokusai Electric is a very strong player in batch process equipment, especially for deposition, and absorbing them would have dramatically strengthened AMAT's market share. But the failure of that deal is a potent indicator of the global regulatory forces that were already at play years ago.
Okay, so that's pillar one, the heart of the company. Let's move to pillar two, Applied Global Services, or AGS. If pillar one is the engine, AGS sounds like the indispensable support and maintenance crew that keeps the entire global system running.
That's a great way to think about it. AGS is the company's moat. It's what protects their business.
Also,
Well, chip fabrication, plants fabs, they run 24/7. They never stop. And every single piece of equipment we just discussed is hugely complex and prone to microscopic failures. The AGS sector is entirely focused on maintaining, upgrading, and servicing that massive, expensive installed base of equipment all over the world.
and I'm guessing this is the high-margin recurring revenue stream. It must stabilize the business when equipment sales fluctuate.
Absolutely. When a fab like TSMC or Intel spends tens or hundreds of millions of dollars on a machine, they need a guarantee that it will run 99.9% of the time. AGS provides that guarantee through installation support, warranty extensions, and crucially, long-term maintenance contracts.
So they're locked in.
They're locked in. And AGS also operates a significant business selling new and refurbished equipment components, which is another steady source of income.
But the sources say the real value add isn't just fixing things when they break. It's the constant cycle of improvement.
That's the key differentiator. They provide crucial upgrades and enhancements for existing machines. They can take a machine that was installed 5 or even 10 years ago and update its software, retrofit it with new components, or even modify its process kit to enable new manufacturing recipes for newer chip designs.
So that extends the life and the capability of the client's multi-billion-dollar fab investment.
Exactly. And it ties the client even tighter to AMAT's ecosystem.
The outline also mentions that AGS includes automation software. What's that about?
Running a modern clean room is a logistical nightmare. You have thousands of precise process steps, handling millions of valuable wafers moving between hundreds of machines. AGS provides the automation software necessary for scheduling, logistics, yield management, and process control.
So it's a brain of the factory.
It is. This software layer is what ensures maximum efficiency and allows the manufacturer to run with minimal human intervention, which reduces error and contamination. It's a huge value add.
So we have the cutting-edge technology in Pillar 1, supported globally by the high-margin services of Pillar 2. That leaves Pillar 3. Display and adjacent markets, the screens we all look at every single day.
Right. This segment really came together after they acquired a company called Applied Films Corporation in mid-2006, and they combined that with an existing unit they had that was focused on large area processing.
What makes AMAT a natural fit for the display market? I mean, huge glass panels seem so different from tiny silicon wafers.
On the surface, yes, but the underlying processes are remarkably similar, just scaled up to a massive size. Manufacturing TFT LCDs, thin film transistor liquid crystal displays, which form the backbone of monitors, tablets, and TVs, requires the exact same foundational technologies as making chips.
Really?
Yes. They use cleanroom environments, they rely on photolithography to pattern the transistors onto huge glass substrates, and crucially, they use chemical and physical vapor deposition to lay down the thin films.
So it all comes back to their core expertise in deposition.
It all comes back to deposition. AMAT simply leverages its world-leading expertise in high-precision deposition and coating systems and adapts them from 300-millimeter wafers to massive glass panels that can be several square meters in size.
It's a perfect illustration of how deeply rooted that core technology is across different fields. That gives us a fantastic summary of their operational structure. Now let's rewind the clock and look at the narrative of how they built this structure, because their history is really marked by chaos, some very sharp strategic shifts, and as we've hinted, some major regulatory roadblocks.
Here is where the story gets really interesting. Applied Materials was founded way back on November 10th, 1967 by Michael A. McNeely and others. They were part of that first big Silicon Valley boom.
And they went public pretty quickly.
They did. They went public on the then new NASDAQ exchange in 1972. But the early years were not a smooth ride to the top. There were some real challenges.
What was the main problem?
Diversification, or really a lack of focus. The initial company sort of drifted into various other ventures that were outside of their core equipment business.
They spread themselves too thin.
Exactly. And the critical turning point came in 1976 when James C. Morgan took over as CEO. He recognized this immediately. He saw that the company needed to commit entirely to the one thing they were best at: semiconductor manufacturing equipment.
And that single decision to narrow the focus seems to have defined the company's entire trajectory for the next 40 years.
It did. The financial results were immediate, and they completely validated his pivot. By 1978, just 2 years after Morgan's decision, sales had increased by a substantial 17%. That one act of strategic clarity basically rescued the company and set it on the path to becoming a global leader.
That focus eventually allowed them to innovate. And the high watermark of their early innovation has to be the Precision 5000 in 1987. Why should we care about a piece of CVD equipment from the late 80s?
Because the Precision 5000 didn't just perform a process better, it revolutionized the entire factory floor. It changed the whole concept of manufacturing.
How so? What was it like before the P5000?
Before the P5000, different process steps required moving the wafer between highly specialized, isolated, single-chamber machines. You do one step, take the wafer out, carry it across the clean room in a cassette, and put it in the next machine.
Which sounds inefficient and risky.
Extremely. Every time you handle the wafer, you risk contamination from dust particles, which can kill a chip. The P5000 was a massive conceptual leap. It incorporated diverse processes, like multiple different processing chambers, into a single integrated system with a central robotic handler.
So instead of transporting the wafer across the factory floor, they could complete complex sequences of steps all inside one machine, under vacuum.
Exactly. This drastically reduced handling, which cut contamination, increased precision, and significantly boosted the yield. It was the birth of the integrated process platform concept, which is completely standard today.
And it was a big deal at the time.
A huge deal. It was so influential that in 1993, the Precision 5000 was inducted into the Smithsonian Institution's permanent collection of information age technology.
Wow. That's a testament to its impact.
It really is.
At the same time this was happening, AMAT was also showing incredible foresight by aggressively pursuing global market expansion long before many of its American competitors.
They were true pioneers in that respect. They recognized the rise of Japan as a manufacturing powerhouse, so AMAT became the very first U.S. semiconductor equipment manufacturer to open its own technology center there, back in 1984.
And they were early in China, too.
Very early. Crucially, they were also the first semiconductor equipment company to operate a service center in China. This early, deliberate global vision positioned them perfectly for the massive scale of manufacturing that would eventually migrate to Asia. They saw where the world was going.
Before we delve into their big strategy of acquisitions, we should probably pause for a moment on that bizarre and unique detail the sources included. The 1992 lawsuit involving Applied Scholastics and Scientology.
It's a strange corporate footnote, for sure, but it shows some of the management challenges that can pop up during periods of hypergrowth.
So what happened?
AMAT ended up settling a lawsuit for an estimated $600,000 with a group of former employees. They complained that they were essentially driven out of the company. Their issue was with some mandatory workplace training courses that were being taught by a group called Applied Scholastics, an organization that has associations with the Church of Scientology, which had been hired by AMAT.
It's a culture clash.
A big one. It's just a moment of corporate turbulence that reminds us that even these highly focused technology companies can sometimes struggle to manage their internal culture, especially during periods of rapid expansion.
Okay, that detour aside, let's get back to the core strategy that defined their growth acquisitions. By the mid-1990s, the company was using its capital to strategically fill in any capability gaps they had.
Yes, specifically around that idea of yield enhancement, which we discussed earlier.
That 1996 acquisition of the two Israeli companies, Opal and Orbat, seems like a textbook case.
It is. They weren't just buying more deposition tools, they were buying control over the whole process. Opal provided high-speed metrology systems, and Orbat provided inspection tools for patterned wafers. These buys ensured that AMAT could offer the full lifecycle solution, the tools to build the chip and the tools to verify its quality.
And that pattern just continued, right?
It did. We see them purchase E-Tech Systems in 2000, then Oromir Semiconductor equipment in 2001 for about $21 million, which brought them new laser cleaning technologies. And then the really big one we mentioned earlier, Varian Semiconductor in 2011.
And the Varian deal was transformative.
Completely. Because it gave them that key ion implantation technology, it meant AMAT could now provide the tools for deposition, etch, polishing, inspection, and the fundamental electrical doping process. It solidified their status as a single-source solution provider for many of the core fab steps.
Their motto became pretty clear. If we don't own the best tool in a critical segment, we'll just buy the company that does.
Precisely.
That relentless pursuit of capability brings us to the really dramatic failed mergers, which I think reveal the true regulatory boundaries of this business. The first major attempt was the planned merger with Japan's Tokyo Electron.
This was a colossal attempt at market consolidation. It was announced in 2013. The combined company, which they were tentatively going to call Iteris, would have been valued at $29 billion.
It would have created an undisputed #1 global dominant supplier.
Without a doubt. They were trying to become the Microsoft of the semiconductor equipment world.
So why did the birth of the largest equipment supplier in history fail?
Antitrust concerns. Pure and simple. After nearly 2 years of regulatory reviews, the deal was officially scrapped in April 2015.
What was the specific problem?
Regulators across multiple jurisdictions, the US, Europe, and Asia, all feared the insane level of dominance the merged entity would have in critical sectors like deposition and etch. They basically concluded that this level of concentration was unhealthy for competition and for innovation in what is a foundational global industry.
So they learned their lesson, but they tried again a few years later with a more targeted purchase of Kokusai Electric.
Right. The intention, which they announced in 2019, was to buy Kokusai Electric, a former Hitachi Group member, for $2.2 billion.
Still a big deal, but not as massive as Tokyo Electron.
Exactly. It was a critical acquisition aimed at strengthening their deposition portfolio, particularly in batch furnaces. But they ran into the exact same wall, only this time, the blocker was explicitly geopolitical.
And the sources are very clear on this. The deal was terminated in March 2021, specifically due to delays in receiving approval from China's regulator.
And that is a huge signal about the shifting landscape, a massive signal.
How so?
Well, think about the difference. In 2015, the Tokyo Electron deal failed because of traditional Western antitrust concerns about market competition. By 2021, the Kokusai deal failed because China, which had by then grown into the largest market for many of these companies, asserted its own regulatory power. They just delayed the approval until the transaction deadline expired and the deal collapsed.
So the foundational technology space had officially become a political football.
It had. And that failure to execute their M&A strategy is a perfect segue into one of AMAT's most ambitious and ultimately most costly strategic diversifications, their foray into the solar industry.
Right, the Energy and Environmental Solutions, or EES, sector, the solar chapter.
This is a fascinating case study in trying to apply your core competence to a new market and just failing dramatically. Applied Materials truly believed that their world-leading expertise in high-precision deposition and coating systems could be pivoted to solve the complexity of large-scale solar panel manufacturing.
They entered the solar market around 2006 after acquiring Applied Films, and they quickly ramped up their commitment, organizing everything under this new EES sector.
Their entry was incredibly aggressive and very expensive. They spent heavily on acquisitions,
Like what?
like the 2007 purchase of HCT Shaping Systems for $475 million, which brought them wafer sawing tools. Then in 2008, they bought Italy's Bacchini for $330 million, which specialized in the metallization steps of making solar cells, printing the conductive silver lines onto the cells. They were trying to build a full-stack solar manufacturing offering.
And the centerpiece of this whole ambition was something called the Applied Sun Fab line.
The SunFab was a visionary concept, announced in 2007. It aimed to apply silicon thin film layers to huge glass substrates, effectively creating photovoltaic modules using the same deposition techniques they use for displays.
And it got some recognition, right? The technology was seen as legitimate.
It was. The SunFab line was certified by the International Electrotechnical Commission, the IEC, in 2009. For a moment, they looked like industry leaders. They even topped VLSI Research's list of PV equipment suppliers in 2008 with sales of almost $800 million in that segment.
They also went all in on the R&D, opening that massive solar technology center in Xi'an, China in 2009.
It was noted at the time as the world's largest commercial solar energy R&D facility. They were not messing around.
So, if the technology was recognized and the investment was massive, why did the whole thin film bet collapse so spectacularly?
The market just shifted way faster than AMAT could adapt. Their entire EES strategy was predicated on the belief that their thin film technology would become the low-cost standard.
But it did.
No. Intense global competition, especially from Chinese manufacturers, drove down the cost of the competing technology crystalline silicon far faster than anyone expected. The economics for the SunFab line just fell apart. The cost to manufacture their thin film panels became completely unsustainable compared to the cheap crystalline silicon flooding the market.
And that forced a rapid and, I imagine, a very painful strategic retreat.
It was. By 2010, just 3 years after the SunFab's big launch, AMAT announced they were abandoning the thin film market entirely and closing the whole division down.
And they kept cutting from there.
For years. In 2015, they left the solar wafer sawing and ion implantation businesses. The process was finally formalized in July 2016 when the EES sector ceased to be reported separately in their financials. It just got folded into corporate and others.
So what's the big lesson here? What that tells us is that while AMAT possesses this unparalleled expertise in deposition tools, they can't just pivot that success into a new, fundamentally different market without major consequences.
It's a massive lesson in staying within your core competency, even when you see what look like shiny, adjacent opportunities. They were punished financially for straying outside the high-margin, hyper-complex world of integrated circuits and high-end displays.
That strategic focus that James C. Morgan demonstrated back in 1976 really is paramount to their success.
It is.
But when we look back at that core business, the resilience and growth are just undeniable. And that brings us to the financial context of their current geopolitical battles.
The financial trajectory is staggering. It just reflects the ever-increasing global demand for digital infrastructure. If you look at their overall revenue from 2005, it was around $7 billion.
Okay.
It vaulted to over $27 billion by 2024. And that growth isn't just volume, it's complexity. Each new generation of chips requires more specialized, more expensive equipment from AMAT, which just boosts their top and bottom lines.
And fiscal year 2021 was a banner year. It really illustrates that explosive post-pandemic demand for chips.
A huge year. Revenue hit $23 billion, which was a massive 34% increase over the previous year. And earnings soared to almost $6 billion. This kind of consistent financial performance is why they're always highly ranked, like being named one of Fortune's world's most admired companies in 2018.
So they were riding the absolute crest of the wave.
They were. High demand, combined with their irreplaceable technology, created a perfect storm of financial success. However, that enormous global dependence and their huge exposure to Asian manufacturing markets is exactly what makes them so fundamentally vulnerable to the geopolitical headwinds that are defining global trade right now.
Okay, this is it. This is where the story of the quiet equipment maker slams directly into the headlines of national security. Let's start with the market reaction in August of 2025.
That event was a really stark reminder that even the most indispensable companies are not immune to political risk. In August 2025, Applied Materials shares tumbled 12% in a single day. It was after the company issued unexpectedly weak sales and profit forecasts, and they didn't hide the reason. They explicitly cited U.S.-China trade tensions as weighing heavily on both demand and, critically, on their visibility.
Visibility is the key operational term here, isn't it? It's not just that sales are slowing down, it's the uncertainty.
Exactly. If you are selling a multi-million-dollar piece of equipment that is subject to immediate export control changes, your customer, a fab in China or South Korea or Taiwan, cannot confidently place an order.
Because a license could be revoked overnight, or a whole category of equipment could suddenly be sanctioned.
Right, and your forecasting becomes impossible. The entire capital expenditure cycle for a fab operates on 5 to 10-year horizons. Geopolitical risk completely scrambles that planning. If the U.S. government restricts the export of your advanced ALD or CMP tools, the client might just cancel the purchase entirely rather than risk buying a multi-million-dollar paperweight.
And that uncertainty is amplified by the ongoing and incredibly serious legal issue that surfaced in 2023. The U.S. Department of Justice criminal investigation. Yes.
This is no longer just about trade tariffs or weak forecasts. This is about alleged criminal circumvention of U.S. sanctions.
This investigation raises the stakes dramatically. AMAT was reported to be under criminal investigation for allegedly routing specialized semiconductor equipment to a very specific Chinese company.
Semiconductor Manufacturing International Corporation, or SMIC.
SMIC. They allegedly did this via intermediaries in South Korea to get around U.S. export controls.
So for our listeners, we need to really understand the significance of SMIC. They aren't just any company.
No. AMAC is China's largest and most technologically advanced state-backed foundry. It's a national champion. For national security purposes, the U.S. government has placed significant restrictions on the transfer of any equipment that would allow SMIC to advance to more cutting-edge nodes.
We're talking about roughly 14 nanometers and below.
Yes, the kinds of nodes that are crucial for advanced military applications and high-performance computing. So the U.S. policy is designed to create a technological ceiling, preventing SMIC from getting the most advanced tools, particularly the deposition and etch tools, where AMAT dominates.
That's the policy.
So if AMAT allegedly routed equipment through South Korea, how would that even work?
Well, it generally suggests a pretty sophisticated attempt to get around the export controls. This could involve things like mislabeling the ultimate end user on shipping documents, routing the equipment through a subsidiary, or even a shell company in South Korea that acts as a front.
Or maybe selling older generation tools to a non-sanctioned company, knowing those tools would then be illegally transferred or maybe even upgraded to perform advanced functions once they reached SMIC.
All of those are possibilities. The core of the allegation is that AMAT may have knowingly facilitated the transfer of sensitive control technology to a designated entity on the U.S. entity list.
The gravity of this just cannot be overstated. We're talking about potentially violating U.S. national security sanctions. What are the potential consequences if these allegations are proven to be true?
The implications are massive. I mean, beyond potentially facing enormous criminal fines that would dwarf any past settlements, AMAT could face crippling new restrictions on its export licenses.
Which could impact their ability to sell even non-sanctioned equipment globally.
Right. Or, in the most extreme case, you could even see executives facing prosecution. This investigation confirms that this equipment manufacturer is no longer just a commercial tech company. It is operating directly on the front lines of technology and national security policy.
And those two major failures, the failed Kokusai merger in 2021 because of Chinese regulatory obstruction, and now the 2023 DOJ investigation into circumventing U.S. controls, they seem inextricably linked. They're caught in this geopolitical crossfire.
They are caught in what you could call the technology squeeze. They are simultaneously too globally essential for either side to ignore, yet too politically sensitive to operate freely.
China blocked their acquisition attempts, flexing its power as a massive market.
And the U.S. government is investigating their sales practices, flexing its power as the regulator of foundational American technology.
So their management team, led by Gary E. Dickerson as the CEO and Bryce Hill as the CFO, they are navigating what is arguably the most complex and risk-laden environment this specialized equipment sector has ever faced.
It requires them to constantly manage the intense technological demands of their clients while ensuring compliance with a constantly shifting matrix of export policies. And these policies are designed not just for commercial fairness, but for strategic competitive advantage on a global stage.
It requires not just technical prowess, but incredible political agility.
And it forces them to make really tough decisions. Where do you invest your R&D dollars? Who can you legally and safely sell to? And what level of risk are you willing to accept as these two global powers continue to fracture the global supply chain?
So let's try to synthesize everything we've uncovered about Applied Materials. We've traced their path from a young company that was saved by James C. Morgan's strategic refocus back in 1976
Right.
through the technological triumph of the Precision 5000 and their strategic attempts to dominate the market through acquisitions.
And we define their technical dominance, that semiconductor product sector, which provides the irreplaceable tools for ALD, CMP, and ion implantation that enable the 3D structures of every modern chip.
We also examined the stability provided by their Applied Global Services division and the strategic failure of their ambitious but ultimately misplaced pivot into the solar energy market.
The essential takeaway here is that AMAT remains absolutely foundational to the entire electronics ecosystem. They are the toolmaker that defines the very limits of what can be fabricated in modern chips and displays.
But that foundational role is precisely what makes them a central player and a target in today's high-stakes geopolitical competition.
And this raises a really important question for you, the listener, to think about further. We know that specialized equipment manufacturers like Applied Materials are indispensable to global chip manufacturing, yet they are increasingly becoming tools of statecraft. We see it with the failed Kokusai deal and the 2023 DOJ investigation.
So what does this concentration of foundational manufacturing technology really mean for the future?
Right. If true technological progress is held hostage by a handful of machine suppliers who have to operate under the increasing pressure of national security restrictions, can global technological independence truly be achieved? Or are we just entering a new era where all advanced technology is subject to the geopolitical whims of the few who make the machines? It's a profound question about the fundamental vulnerability of our entire digital age.